Hello, everyone. Welcome to our talk, Feasible Open Source Remote Attestation for the Edge. I'm Michael Peters. This is Sturmann, a co-presenter. We're both engineers at Red Hat in the emerging tech team, specifically working on security and trying to solve security problems. So, since this talk is about the convergence of multiple things, software security, hardware security, edge, fleet management, we want to make sure that we're all a little bit on the same page when we're talking about this. So we're going to take some time to define the problem space a little bit, talk about what attestation is, why it's used, and how. And then we can talk about how we solve it for our specific use cases, and then what we still need to do. And then we'll talk about how this fits into conversations that are happening in the industry today and what the future might look like. So when we talk about attestation, simply put, it's the use of cryptographic techniques to verify the integrity and authenticity of digital assets. So this involves signatures, measurements, public keys, chains of trust, that kind of stuff. But essentially what we're trying to do is answer questions like, what entities produced this software product? Has the system been tampered with? Can we prove or make some guarantees that something happened at a specific time?
So, as some of you may know, attestation is a somewhat overloaded term. It's broadly used in the industry because it's very useful in many specific domains. And so while people may use it to refer to their own specific domain within security, we want to make the point here that it is broadly applicable and also kind of disambiguate how we're going to talk about it in this talk. For example, we talk about attestations a lot in the confidential computing world because by definition, confidential computing does rely on attestations and knowing the integrity of the system in order to know that you are running in a confidential space. But attestation is useful beyond just this environment. So we can have attestations as well that we use to prove a system's integrity when there's no confidential aspect involved. We just need to know for security reasons that the system is still running in the state that we expect. And similarly, attestations are also important in software supply chain security, where they involve signed metadata about some software artifacts or packages that are going to be part of a build system and end up in the end resulting product or application. And so each of these attestations might look slightly different from each other. So in the confidential computing world, they're going to look slightly different from in the supply chain world. And then what we're focusing on today is actually the remote attestation for integrity without confidential computing. And these attestations need a hardware root of trust, which we'll get into. And that root of trust is generally going to be something called a TPM. We'll explain that in a moment. But we wanted to kind of illustrate as well that these types of attestation do fit together. There are some overlaps. And so, oops, don't want to advance yet. Basically, we see here on the left, we have software supply chain attestation. So these are the signed metadata and especially the signatures on the packages, the artifacts, and everything that goes into what will become a running system or something that's deployed somewhere. So when you get to the end of that arrow, you have this friendly green computer that represents a running system. And at that point, we get into boot attestations and runtime attestations. And those can be done locally, but what we're going to be focusing on today is how to verify those boot and runtime attestations remotely. So when the computer is not actually physically with us, it's in the cloud, it's on the edge, how do we do that? And what does that attestation process look like? How do we enable it? So one of the things that differentiates remote attestation from something like supply chain attestation is that we need a hardware root of trust. This is necessary on a running system because we have to trust something to give us a report of that system's current state. So we generally like to have this in hardware because it's more tamper evident than software and it's more difficult to compromise. So for example, the software running on a system can be maliciously altered more easily than a hardware root of trust can be made to create a false attestation report. And the hardware root of trust that we're going to
sorry about the slides, that we're going to focus on here, because we are not talking necessarily about confidential computing, is a TPM. Thank you, Michael. So this is a chip that is fairly common on various types of systems, and it has some interesting and robust security properties. So among other things, it helps keep track of system state by using concatenations of hashes in a structure called a Merkle tree. So each of these hashes or measurements depends on the one before it, and this makes it harder to forge or alter the record of events that took place on the system. The TPM keeps these hashes in registered called PCRs, which will come up later, and it can produce a record of them in a signed quote. So, yeah, and it also has its own hardware private keys that are not accessible outside the chip, so that's an important security property. This other image you see here is a CPU, so that's a hardware root of trust for confidential computing. That is out of scope for us here, but we just wanted to set the stage that there are different types of hardware that can be used for this hardware root of trust. And loosely, you can think of the hardware root of trust as similar to a CA in an X509 certificate chain, because it signs off on everything else downstream of it, and it is the ultimate guarantor of trust for that system. An important side note is where hardware TPMs are not available, you can use cloud or virtualized TPMs, but you are then including the vendor in your trust model. So this is a little bit less robust, but it allows for the option to expand attestation to these environments.
So when we're talking about our software ecosystem and this attestation, we have links in this chain, and each link needs to be connected for a full solution. The chain starts with our software supply chain, as Lily mentioned, and it continues all the way through boot. It extends up through the runtime of our system and protecting the integrity of every file on our system. This can also include parts of your build pipeline that produces a software supply chain, where you're measuring the actual nodes that are doing the software and recording the attestation properties there, and also to be able to do audits and things like that. But when we can prove the secure state externally, that also opens up other branches that can be built on this tree, such as our container runtimes and workload identity. So all systems are complicated and will likely have multiple roots of trust that are linked in different ways. So it's important to understand how your system is built and where you are placing your trust in that system and how things are connected. Some parts will be more or less secure. For instance, like an immutable system is going to be less complex and more secure, so the chains and roots of trust will be simpler. Some can be very complex and require more care in how they're linked. So it's important to note that your software at the very end of the tree, or the root leaves of the tree, can never be more secure than the layers below it. So Lily talked about a hardware root of trust and how we're going to be basing that, and those attestation techniques can be used when you're doing things locally. And they should be applied at that level, but it's not enough for most enterprise applications. Remote attestation is the ability for a remote third party to independently prove the cryptographic evidence is true. So a secure system might use attestation to prove to itself that it hasn't been compromised, but it's rare that a system only interacts with itself. It needs a way to prove to the larger network of systems that everything is okay. So if you have some shared secrets, sensitive data, sensitive workloads you want to be able to release to a target system, you need some way to independently prove that that system hasn't been tampered with, and you can't just rely on self-reporting. Local attestation policy are nice for a layered approach to security, but if we can't prove it, then our trust ends there.
So where might we need remote attestation? We don't need it everywhere, but in scenarios that require higher security, because things can go really wrong when a machine is compromised, it can be very useful. So this is a concrete example we wanted to illustrate here to focus on. And some of you might have heard of a new technology that's popular right now called AI. And one area where AI is being used is at the edge, or devices located outside of data centers, loosely speaking. So the scenario illustrated here is, let's say, a robot, but in reality this would be probably thousands of these little robots, and it's clearing away some rubble after a disaster. So it's got an important job, it needs to do it accurately and quickly, and we want to ensure that this device starts off with the right software running, so it's got the software supply chain integrity, but then we also want to make sure that as it runs, it's not going to be compromised to do something counterproductive to its goals. And if it is compromised, we want to know about it relatively quickly. So one of the challenges is that in this type of scenario, even though security actually becomes more critically important, it's actually harder to secure these types of devices a lot of the time because they don't have the physical security of being in a data center. And especially as we look beyond this specific example, we have a lot of use cases in critical infrastructure and manufacturing where we have these types of challenges, and we want to be able to secure those workloads and devices and just make sure that they keep running the way that they're supposed to. So tools do exist to do this, including Keylime, which we'll talk about shortly. But there are numerous challenges in applying the principles of these tools and being able to use them in real environments, like the one illustrated a moment ago. So it's not as easy as just firing up a verifier and saying, tell me whether my remote system is compromised. And a big part of this is that the tools can't make our trust decisions for us. This is a broader challenge that shows up in many places in security beyond attestation. But we have to be able to tell the tools what to expect our system state to be, and we have to be able to codify that somehow in a way that's meaningful, reproducible, and accurate. Another challenge that we touched on a moment ago is the environment where this is most useful is often challenging. We have questions of scale. We have questions of limited connectivity at the edge, so we can't always ping the device whenever we want to get it to report on its integrity. And additionally, we also need to be able to understand what a passing or failing attestation means. We ideally want this to be auditable, and that means somebody needs to be able to interpret it. This can also be very challenging. And then, of course, on top of all of this, systems aren't static, so how are we going to deal with change in a real-life scenario? When we're not just firing up a toy system and saying, okay, great, we've attested it, how do we deal with system updates, and how do we meaningfully discern legitimate change that should be allowed versus a malicious change that shouldn't have taken place? So regarding this first set of challenges, we need to define something that we're calling policy. Policy, even more so than attestation, is a very broad term. You can have policy, you can even have security policy about an infinite number of things. But when we talk about it here in this talk, we are going to be using it to describe what should and shouldn't be on the system. There is a related concept called reference measurement that we'll get into shortly. And we may also use this word incidentally to talk about actions that we want to take as a result of attestation being verified, like passing or failing. But for the most part, we're going to be talking about it, describing what we want to see on the system. There are many ways to express this type of policy in a lot of different formats and tools, which will lead us into the standardization work that is ongoing in this area.
The first part of this is the policies is having reference measurements. So this software can pretty easily be identified by taking a cryptographic measurement or a hash of the various files of that software component. A mature build pipeline should be able to create these for us, and as we package these measurements together, we can refer to that as a reference integrity manifest, sometimes just reference values. And there's sometimes things we want to ignore, like on most systems they have files that change, log files, user directories, volatile configuration, things like that. Another way to be able to identify the policy of what we want on the system is to be able to use file signatures. So file signatures allow us to prove the provenance of where the file came from, and the Linux extended file attributes allow us to embed these signatures into the file itself. And this is really useful for files that could be very specific to that machine, so configuration files, keys, that kind of thing. And it can also be useful when there are systems that have a lot of files that we don't want to keep track of every file. In some ways, this can seem easier to manage because as a consumer of this, you just care about a limited number of keys that have signed things, and you don't have to deal with a whole boatload of all the measurements for every file. But it's a little bit of misleading to say that because somebody has to manage the keys somewhere, even if it's not your team. And this is also a little bit vulnerable, or this is vulnerable to rollback attacks. So for instance, if there's a, say, your OS vendor signs their particular release of OpenSSL, and then later there's a serious vulnerability that's found in that version, your OS vendor produces a new package and ships it out, you install it, but an attacker decides to install the older version. It's still going to pass attestation if all you're relying on is signatures because they were both signed by your OS vendor.
So getting into what's so difficult about these policies or reference measurements, you would think that if you are able to have an attestation system, you can turn it on, check that your system hasn't been tampered with, and that's it. If only it was that easy. So as we touched on earlier, you need to be able to define and codify the system state. So you need to explain what is included in that state and what's not included. You might not be measuring the entire system. You need to have a format that describes, what comes first, second, and last. Do pieces depend on each other? What's the level of granularity? So this is a challenge that has been tackled somewhat in the ecosystem, but what's actually potentially more important is if you have a predefined format you can use, you actually still need to collect the reference measurements from somewhere or generate them yourself. So this is really kind of the crux of one of the problems that we're investigating, which is that reference measurement collection is pretty difficult. There are 3 general ways that you can do this. So ideally, the best way would be to get them from build systems. And this is ideal because you can measure as soon as some software is packaged, so there's less chance of the measurement being altered between when this is created and when it's measured. But of course, if you aren't the owner of the build system and you're not the one cranking out this software, you can't actually do this. So you're reliant on someone else to be able to generate and provide these measurements to you, which is not really common practice today. Now, if you don't have access to that type of measurement, you can try to generate it yourself in one of 2 ways. The first is called golden measurements, and this is basically a test run of your system in an isolated, secure environment. So you try to get a clean install and boot, and then record the system state with the assumption that it's in the state that you want it to be in. And then you compare against that value in the future when the system is actually running in production. But if you're not able to do that, then what you have left is basically trust on first use, or TOFU. So maybe you don't have an isolated environment, you can't do a test run. You're going to have the system come up, and the first time that it comes up in whatever state it's in, you're going to assume that that's the known good state. That's what you're going to use for your reference measurement. And this is a little bit less secure. You don't know for a fact that it hasn't been tampered with when it first comes up, but you can guarantee against future unexpected changes. So those are the 3 ways that we're kind of looking at how we can get these values. But it is very complicated. There are still challenges. For example, if you have 2 very similar systems, you can't easily just alter one part of this measurement. You usually have to measure the entire thing. It's very difficult to mix and match. And of course, as we know, stacks can be very complicated. You've got a lot of combinations of operating systems, configurations, applications, rotating secrets, so on. And even then, of course, as we mentioned, that's only the first step. You're going to have system updates, you're going to have changes. You need to be able to know which changes are legitimate.
So this is where Keylime comes in. So as Lily mentioned before, Keylime is a CNCF project for remote attestation. It started as a white paper out of the MIT Lincoln Labs in 2016. And it basically uses a host's TPM and the Linux integrity measurement subsystem to provide measured boot attestation and file integrity attestation. And it's a public project on Keylime. on GitHub. So to step back a little bit and talk about this integrity measurement architecture. So this is a subsystem of the Linux kernel. And what it provides is that every time a file is executed, the parts of that file, so the binary, the libraries that are loaded, they're measured by IMA in the kernel. And this hash, which is usually SHA-256, is extended into a PCR in the TPM. As Lily talked about, this hardware Merkle tree that we have. So this root node Merkle tree, and we have a hash of hashes. So the measurements are also logged by the kernel in a separate location and can be retrieved, and you can compare the two. So how Keylime works to accomplish this is that it takes all of this attestation data, the log measurements, the quotes of the PCR values from the TPM and other things, and sends them to a Keylime verifier. The verifier validates the signed PCR quote of the TPM, validates that it's from a trusted vendor that you have in your certificate store, and then it reconstructs this hash of hashes using the IMA log and compares the two. And if the final measurements match the PCR values, then we know that the IMA measurements haven't been tampered with. And then we have an accurate record of every file that's been executed on that machine since it booted up. Keylime then compares this IMA log against the reference measurements from our policy to make sure that every file is exactly what we want it to be. None have been changed, no unauthorized files are executed. And if we find something that shouldn't be there, we trigger an error. So currently, this is what the general Keylime architecture looks like. We have an agent that's installed on each target node. That agent communicates with the TPM and gathers the attestation evidence. We have a tenant, which is a CLI tool that does the initial agent onboarding. It does a cryptographic identity handshake with that agent, and it does policy configuration. We have a registrar, which is the public key store for each of those TPMs, and also a database of the registered agents. And then we have the verifier, which polls each agent for evidence and validation of that evidence. It also serves as an API endpoint for integration, for verification, agent identity, and so forth. So in the current Keylime model, it's important to notice that the verifier is reaching out to the agents and polling them. So this is what we refer to as the pull model. Keylime is pulling this data from the agent, which, as we'll see talking later, and then we talked about constraints for edge, this doesn't really work for environments that aren't super well connected. So along with this, Keylime has a revocation mechanism to trigger when attestation fails. So Lily talked about having the ability to notice when something is compromised quickly. And so when Keylime notices these attestation failures, it can trigger some sort of mechanism, usually a webhook, that revokes this trust in that system from other parts of the system. And this architecture has proven to be pretty scalable. We've done tests with this into thousands and tens of thousands of nodes that are being attested. But Keylime isn't a user-facing tool. It's behind-the-scenes APIs, so it doesn't really have a cool feature to show when something fails attestation. It's just a failure message in an API or a webhook. But it does drill down. If you can see this at all, in this case, this is a failure where an evil shell script was run, but we can tell that this was a validation of the IMA measurement list and exactly which file caused the attestation failure.
Our other open source project that we're working with is called flightctl. So despite its name, it has nothing to do with aviation. Instead, it solves problems in edge management. So it can manage individual devices or groups of devices known as fleets for their entire life cycle. And this includes onboarding, the entire lifetime of operations, and then also decommissioning at the end of life. Right now, the contributors to flightctl are mainly Red Hatters, but we do want to see this project move towards being a more community-driven project, ideally. It's also in beta, so there's a lot of active development, and we're still building out many features, including our security vision and integration with Keylime. But so this is useful not just in itself, because we want to make flightctl work as well as possible, which obviously we do, but the reason it's interesting here is that it is a good test case for how we can adapt attestation to some of these real-world scenarios and environments. So next we're going to talk about some of the integrations that we've already made between flightctl and Keylime, as well as some of our upcoming work, and then also what we're envisioning and what we'd like to see more broadly to support attestation in these types of environments.
So the edge and flightctl itself has some constraints because the edge just works differently. And these are compatible or incompatible with how current Keylime architecture works. For instance, flightctl already has its own agent, and since some of these edge devices are small and limited, we wanted to not have multiple control plane agents running. All communication with the control plane is done through a special flight control tunnel. So a separate Keylime agent trying to talk to separate Keylime servers just wouldn't work. So we need to make some changes to Keylime. We dropped the Keylime agent and added the TPM communication and evidence gathering into the flight control agent itself. Since flight control is handling device onboarding and registration, we don't need a separate registrar of devices, and so we don't need the registrar. We also don't need the tenant to do the initial identity handshakes. And since flight control is handling the cycle of when to run attestations, we don't have the verifier polling the target nodes. Instead, we have the flight control agent and flight control server deciding when to gather new evidence and to send it, and then flight control server communicates with the verifier directly. But we had to add new APIs to the verifier to allow this. So it's new evidence verification APIs that place the burden on the third party to collect the evidence. So it introduces a new trust model for Keylime. Keylime is no longer assuring the provenance of the evidence, it's just attesting to whether the evidence passes, that it's cryptographically valid and that it passes your policy attestations. So these new integration APIs also allow a couple other new features for Keylime that we weren't initially part of the plan, but that we noticed as we were developing it. So it's pretty common if you have some way of auto-generating policy to try to test that or wanting to be able to test that ahead of time before you roll out into production, which wasn't really possible without setting up a whole new system. But this allows you to have CI/CD pipelines that connect to a Keylime verifier just to say, does this evidence pass this policy? And allows Keylime's evidence and policy engine to be used in other third-party integrations. So combining this together, talking about all this policy stuff that we talked about and all the difficulties with policy, with flight control managing the devices and the device life cycle, this gives us some unique opportunities to generate policy on the fly. So flight control controls the images which run on the devices. In flight control's case, it uses boot C, and we can take these images and recreate the file system that would have been possible or would result from these images, and to create our own reference measurements ahead of time. Flight control also knows what the device looked like at initial boot, so we can gather information from the PCRs and also the boot log to be able to create boot log, a tofu policy for the boot. That's either using the boot log as a template or relying on those golden PCR measurements. So this helps us to get over some of the thornier issues with policy by controlling the lifecycle of the devices through flight control. This also helps with software updates. So as the images change, flight control could adjust, amend, and create new policy before the images are even sent out to devices. Keylime has the ability to use either one-off policies as you're testing, as you send through the API, or it can even use named policies that have been created previously. So this allows the reuse of these images and policies, which can help with scaling. So you don't need to have thousands of per image policies out there. Future working Keylime will include layered policies so that you can stack, for instance, have one policy for a specific OS version and layer another policy on top of that based on the device's use case.
So this is a work in progress, and we've got some exciting steps ahead of us still. But so far, we've already got a Keylime API enhancement proposal that's been accepted, and the implementation based on that proposal is under review. So what that will do is it will give us a more modular version of Keylime, specifically the verifier that we can use to send attestation evidence directly from flight control. And then on the flight control side, we've got some TPM features. Right now they're under an experimental flag, so we need to do some more robust testing. But it can check if there's a TPM on the device, it can collect some basic TPM information, and then it can gather an initial attestation report. So the next steps concretely will include sending the attestation report to the verifier, of course, to have it validated. And then what we'd like to do is to have some type of automatic policy generation or reference value, reference measurement generation, so that we don't just say, oh, this is the user's problem. Because without those reference measurements, validating the attestation is not possible. So ideally, we want to get these values from build systems, as we mentioned earlier. So at least for the higher levels of the stack first, and then we could look into how we could incorporate lower levels potentially, which will be more challenging. So that's enough about computers. We're going to talk about the future of attestation, which is rats. These fuzzy little creatures you see on the screen. RATS actually is the Remote Attestation Procedures for the acronym. It's the RATS architecture, and this is a standard developed by the IETF, which does the really important work of giving us some standardized definitions of attestation procedures. So it defines things like the different parties involved and the communication steps that need to occur and the different pieces of evidence during an attestation flow. So for example, what we've been calling reference measurements would be known in RATS as reference values, which is luckily a very close term. And this will aid also in evaluating attestation tools and comparing them to each other as well, and comparing the guarantees that they can provide, since they're all designed and architected slightly differently. So RATS gives us a common design and architecture language in order to be able to relate these different tools and provide ways to understand whether an attestation is successful and meaningful. So in our work with Keylime and flight control, and as we look more broadly, we are aiming to be aligned with RATS and to basically build out our capabilities and tools in alignment with this standardization, and use the standard also to assess the gaps in the ecosystem and be able to communicate about them and build some community around that. And then basically, as we look at the future of attestation, this is not a very busy slide, but it kind of sums up where we think attestation needs to go. So standardization and transparency are what we think are key ideas here. They need to start in the ecosystem, and then, as mentioned, we need to align the tools that we create with these standards and push for further transparency to make the attestation technologies more usable and accessible. So standardization is important because otherwise it's difficult to have reliable ways to generate or access the reference values or compare the functionality during attestation of the different verification tools, or see if there's interoperability between components. And the standardization work that has been done so far is really great, and it involves things like report formats and responses and the attestation flow itself. But one thing that would be really interesting is to have standardization around the information that reference values should contain and how reference values are generated. It's possible that this is out there somewhere. I hope it is. So luckily, yes, there's been a lot of good work in this area in the upstream ecosystem. I called out RATS in the last slide. There is also a number of organizations that are doing great work in this area, like the Confidential Computing Consortium. So even though we are not working on confidential computing right now, it is all related, and they are doing great work in integrity and attestation in support of confidential environments. There's obviously the IETF as well, and multiple others. And I actually do want to give a plug as well to the OC3 conference that happened a few months ago, because there were a couple of really great talks on this topic around standardization, attestation, and how we can make improvements in the ecosystem there. So it's definitely worth looking those up. This second piece here on transparency is also critical, because this is what enables us to really know the expected state of our systems across the whole stack. So since this is Open Source Summit, I think many of us realize the value of having open information code and components that we can examine. And this is true for attestation as well. So being able to access reference values for the whole stack, potentially down to the lowest layers, including firmware or maybe even the hardware, that would be very exciting. And if you think back to those different methods we had for generating these reference values or measurements, getting them directly from the build systems is the best and most secure option where possible. So these would need to be measurements that are obtained and shared by the organizations who are actually building those components, which is not really common practice today. But that would actually help us a lot in making attestation more accessible and usable, and it would also make targeted attacks much more difficult, which would also be exciting.
So in the vision that we have for an attestation future, as Lily mentioned, these build pipelines are very critical in creating these reference measurements. So we need to be able to have all parts of the system that create software, from the OS vendor to maybe your container build systems or container registries that you pull from. All of these pieces store and record these reference measurements and sign them. So in an OCI registry possibly, or using SIGSTOR to sign the components. We need tools to make this seamless and transparent and automatic. As we talked about, we're trying to do that with flight control because we have a new greenfield project and we have control over the lifecycle management. But we need to expand this into other parts of the system. We need to be able to have these reference measurements published ahead of time to make it way easier to compile these manifests. We need vendors, including OS vendors, like we both work for Red Hat, and we would love for Red Hat to be able to publish the reference measurements of every piece of software we publish. That's a big ask, and we're working towards that. But this is the strategy we hope to align on. Any questions? Yes. Oh yeah, with handheld mic.
So the first question is around that. The last thing around build measurements, which aren't hugely helpful unless you have full reproducibility builds, which, given that Red Hat doesn't expose its build environments, isn't going to be happening, right? So, to what extent is that going to happen?
So you're right. It is more helpful when you can have reproducible builds, but I think there's still a lot of value in being able to say, for instance, this version of this operating system, here are all the possible reference values for the files that could exist as we publish them. And then we sign that manifest, and you can pull it in and verify against your system. It doesn't mean that those values are always going to be the same, right? Different updates and things would change those values. Different build times and parameters could change those values, but it still provides a nice reference that you can go back and compare.
I agree. You're just adding more trust anchors into it, which is not necessarily always very good.
Yeah, that would, first, it would do that. I guess in the spirit of exploration, I kind of see it as like, we have the opportunity to try this with some of these internal build systems, right? But what would really be the goal is to have a way to do this in a very open way so that everyone can see, okay, this is exactly what the build environment was, this is the value I expect, and then this is actually what's running in my system. So that's kind of the dream. We like to dream big, but we have to start somewhere, and yeah, I think you're totally right.
Yeah, it doesn't remove that trust layer in the vendor, right? You still have to trust the vendor, but at least you then have a reference you can compare against.
Don't get me wrong, it's better than nothing. Yeah. I've got several more unless anyone else wants to jump in. Okay. Oh, you want to go? After you.
So this generally produces attestation artifacts, of my understanding, which may be getting standardized and so on. But today, am I expected to implement that myself, or are there any systems that already are consuming those artifacts, such as maybe an orchestration system like Kubernetes, or an operating system? Is there anything already consuming these artifacts to make decisions on it?
Yes. So to answer your first question, do you have to build some of it yourself? Yes. Okay. But yes, there are pieces that do consume it. There are tools like FA Policy D, which can use local attestation to compare and prevent files from executing on your device, for instance, that are not signed by your approved key chains locally. Other things like FS Verity that can also use like hardware roots of trust to verify a file system and things like that locally. But for like a remote attestation system, Keylime obviously, but then Keylime custom creates the evidence, right? So if something is gathering that evidence and not doing it in a format that Keylime wants, Keylime wouldn't understand it. Yeah.
But what I'm saying is, it would make a lot of frankly, you probably don't need to, you could build it as a separate piece of software, especially if it's standardized to not schedule workloads on my unattested machine.
Right.
But is there anything, there's nothing yet in that
There's
space?
not anything currently. I mean, that is part of like our future. Like we see this as, for instance, like a Keylime operator running on a Kubernetes cluster to provide an attestation service, not only just for external things, but also for that cluster to be able to do things like revoke, do a coordinate drain on a node that has been compromised and move. So all of this has been done. You can do all of these things. You just have to do it by hand. Right.
Yeah.
So we do want to automate all that, turn it into an operator, and have it all just seamlessly work together. And yeah, but you're right. It
Yeah,
does.
it's basically just tricky. But even with Keylime, we can say like, for example, we don't want to release some secrets until a certain state of attestation is reached. And I know I'm less familiar with this other attestation tool that we have in Red Hat called Trusty, but I know it does kind of the same thing. It's a key broker service. So it's like you have to have the system in a certain state before secrets are released. And in their case, it is to a confidential environment.
Right, and then further to that, like Trusty is for confidential computing and Keylime is for the integrity attestation. And we are working on integrations between the two as well. So that work is ongoing. Yes. Or, yeah, right behind you. Either way.
Closer. You're closer, yes.
Yeah, I was about to ask you guys about that. But between Trusty and Keylime, do you see those two things end up merging at some point, or are they really as separate pieces you need to keep separately?
I think they're going to be separate, but there's going to be integrations between them. Integrity and confidentiality are just two distinct things. And being able to use like a hardware root of trust based in a TPM versus a TEE, so the trusted enclaves on the CPUs, are very different attestation flows. And so the integrations that we are seeing from just the internal work that we're doing is to have, for instance, in a confidential computing environment, to have the initial attestation work done by Trustee, and then to be able to communicate that with Keylime, or for Keylime, for runtime attestation further on, for Keylime to be able to talk with Trustee and use that as also a source of. So we're not totally sure of how that attestation is going to work, but like Trustee does the initial attestation before the resources are released for compute, but it doesn't do runtime attestation like Keylime would do. And we think that they live in two separate spaces that need to communicate, but don't need to be the same.
Yeah,
thing.
and we're also trying to map both of them to rats. So this is like kind of an active area of exploration that we have. Also, we are in emerging tech, so we are not claiming that anything will be available at any certain time.
Yeah.
But this is something that we are exploring, and it's a really good question.
Yeah, so to speak on this, like at RATS and the standardization work, Keylime and Trustee both predate RATS. So they came up with their flows and stuff and terminology and the way that they package evidence and things like that before RATS came along. So we need to sort of converge towards the standard to make it easier to communicate.
Yep.
All right, sorry, go ahead.
Cool. Systems I would see using this on would also be systems that I would probably want to have full disk encryption running on by default.
Yeah.
I guess are you, in your initial research, are you running into any conflicts with things like FDE and system deboot? Because that's already kind of not playing very friendly with TPM2 at this point.
I guess the answer is not yet, but that is likely to happen, and we need to figure that out. Yeah.
Yeah, and we would, like the way that these attestation flows work for Keylime is that Keylime is after the fact, right? So Keylime gathers this evidence after the machine is already booted up and been running, and then compares it against the running system. So FTE is already working, but you're right, that could complicate how the measure boot itself is logged and generated and that kind of stuff.
Good impetus to improve system deboot.
That could be, yeah, down the right this way. All right. Anyone else?
Can I ask another one? So you talked about changing the semantics of Keylime in this use case, which I don't think I have a problem with, but I'd like to know how you're thinking about exposing that, because it's very important, clearly, that you expose which semantic is being employed for a particular attestation. Have you thought about how that could be exposed either UI level or machine level?
Yeah, so it is currently marked as an experimental feature in Keylime. And one of the big disclosures about that is this changes Keylime's trust model, right? Keylime can no longer guarantee the provenance of this evidence that's gathered. And so I think it's just going to be a big disclosure that if you're using this model, your third-party system has to control device trust,
and how you're building that trust, how you're doing device onboarding, registration, all that kind of stuff. And Keylime's not going to concern itself with that. But it does open up for a lot of other things. So yeah, it's, I think, a little bit of a wait and see how people are going to use it. But we're going to have these huge big disclosures about it. Like, you need to take care of this trust somewhere else. You can't just punt it.
And sometimes you have those sorts of modes where you can move from one to the other. You need to make sure that there's no movement. Once you've gone to one particular use case, you can't move to the other.
There's no back and forth between it. And it's a little bit protected in that you just can't use this out of box. You have to build your own integrations with this. So you have to be thinking, hopefully, about that as you're doing it. It's not, I mean, the APIs exist out of box, but they're not usable out of box with the normal Keyline flows. It's just basically reusing the same policy engine and evidence verification engine internally and exposing that.
Thank you.
Any other questions? All right. Thank you.
Thank you all.